and for hosting our talk. So I'm Georgina Cosma, Professor of AI and Data Science at the Department of Computer Science at Loughborough University. And the work we are presenting today is part of the NIHR-funded project called DECODE. For the DECODE project, I'm leading the work package on developing equitable AI-based solutions for patients with learning disabilities and multiple long-term health conditions. My two research associates, Rania and Emeka, who are working on the project, are also here with me today to present our work. Rania?
Thank you, Georgina. I'm Rania Kousovista. I'm an applied mathematician and research associate in the DECODE project, working on long-term condition trajectories and find their patterns. Thank you.
Yeah. Hi, everyone. So my name is Emeka also, and I'm working with DECODE on the AI aspect. So we're also working on developing a lot of machine learning schemes for adults with learning disabilities. Nice to meet you all.
Thanks, Emeka. Next slide.
Okay.
So there's a group of individuals in our society who face unique health challenges. So it's those with learning disabilities. Over 2% of adults in the UK, or more than 1 million people, have a learning disability. Unfortunately, the life expectancy is significantly lower than the general population. So recent data shows that men with learning disabilities have a median age of 63 years old, compared to 82 for men in the general population. For women, the median age of death is also 63, which is 23 years less than women in the general population. One major contributing factor is that nearly all individuals with learning disabilities, that's around 98.7%, have multiple long-term health conditions with an average of 11 conditions per person. So this includes higher rates of mental health issues, epilepsy, and difficulties maintaining a healthy weight. Next slide, please. So a critical issue affecting people with learning disabilities in the UK is avoidable deaths. MenCap, a leading UK charity, defines these deaths as deaths that could have been prevented with proper healthcare. So in 2013, 38% of individuals with learning disabilities died from avoidable causes, compared to a mere 9% in the general population. Fast forward to 2023, and the leader report reveals that this figure has risen to a staggering 42%. Now, the likelihood of avoidable death varies depending on the severity of the learning disability, ranging from 39% for those with mild disabilities to 3% for those with profound disabilities. So what's causing this disparity? Numerous barriers prevent people with learning disabilities from accessing quality healthcare, including inaccessible transportation, unidentified disabilities, staff misunderstandings, misdiagnoses, patient anxiety, poor collaboration between care providers, inadequate aftercare, and more. So next slide, please. So in today's talk, we are presenting some of the work from the DECODE project. DECODE stands for Data-Driven Machine Learning-Aided Stratification and Management of Multiple Long-Term Conditions in Adults with Intellectual Disabilities. And at the heart of the DECODE project is the innovative use of artificial intelligence and machine learning techniques to develop understanding, strategies, and tools for managing the complex health needs of this population. And of course, when developing these AI methods, we always make sure that they're equitable and fair for everyone. Next slide, please. We've been working with the Secure Anonymized Information Linkage Databank, or SAIL Databank for short. So this is a national trust research environment for Wales that holds both GP and hospital data. So the work we present today includes analyzing hospitalization data to predict length of stay, identifying clusters of long-term conditions in patients with learning disabilities, identifying common temporal patterns and trajectories of those conditions, and we are working closely with our patient and public involvement and engagement team to translate our research into tangible improvements in care and quality of life. So over to you, Rania.
Thanks, Georgina. So today I'll speak about how we prepare the SAIL dataset, the definition of a long-term condition, and the patient characteristics included in this study. Next slide, Emeka, thank you. A few words about SAIL. SAIL is anonymized patient-level data from hospital and GPs across the Wales. SAIL contains data for more than 3 million patients and found learning disability patients to be 14,323 over the Wales. And approximately from this number, approximately 13,000 long-term condition patients found to have at least one long-term condition. Next slide. So let's have a look how we prepare the SAIL dataset with a focus on this population. As I mentioned before, we identify patients based on learning disability codes, included patients that are adults and had registration in a GP. First of all, a professional advisory panel, including clinicians, epidemiologists, psychiatrists, and other experts in learning disabilities, was formed in order to provide us guidance and give us feedback on various aspects, and including the list of these long-term conditions that's associated to this population. In addition to that, professionals of PPI groups meetings, including 3 groups of experts by experience with people with learning disabilities, family and carers in those people help us in order to finalize this list. Thus, from the initial 110 long-term conditions were chosen 14 long-term conditions, in which some of these were combined together under the same group. One example is the schizophrenia and severe depression were grouped under the mental illness disorder. And then we identify the ARID and ICD codes for these long-term conditions. Of course, we revise and clean carefully these codes because in the phenotypes there are many irrelevant codes. In addition to that, medication and other risk factors were included and extracted from the database, as well as the mortality data. Final, in the previous slide, Emeka, sorry. Final, we conducted a thorough analysis of the number of the records, and we obtained separate tables for GP and hospital tables that we merged together and harmonized these tables into a long table by creating a new variable that harmonized the 2 coding systems, read and ICD codes respectively. At the end, we apply several duration criteria to conditions that weren't defined as chronic initially. Next slide, please. In general, a long-term condition is a condition that cannot be cured or treated, like diabetes, hypertension, and others. But for conditions like constipation that can be either acute or chronic, we followed the process outlined in this flowchart. To begin with, for each patient, we searched for 11 codes, either read or ICD codes, if they had the chronic in front. For example, chronic constipation. Then we take it as chronic that this patient have the condition of long-term constipation. Otherwise, if no chronic code was found, we looked for 2 distinct events, diagnosis meaning, that are at least X days apart within a window of 1 year period. So if such a pattern was found, then the condition was classified as chronic. In the example of constipation, constipation is considered to be chronic if it occurs more than 3 months within a year. So in conclusion, patients that meet either the chronic code or the 2 events criteria presented were considered to have a long-term condition and were included in the study. Otherwise, we exclude these records because our study focuses on long-term conditions with learning disabilities. Thank you, Emeka. Next slide, please. As we covered how we prepare the dataset, we can have a look in the data characteristic of the patients. First of all, in the characteristic presented here, we take the most recent records available for each patient for this population. We can see for gender that the distribution is fairly balanced, with 47% to be females and 52 being male. Also, about age, the distribution shows that most of the patients were middle-aged or older. And in addition, in the terms of ethnicity, a significant majority of the patient males were white, among 70%. And we need to note that 27% of these patients had a known ethnicity. Last, looking on the deprivation index, we see that the larger proportion of the patients, 28%, fell into the most deprived quantile. I will now pass it over to Emeka that discuss about hospitalization patterns. Emeka, over to you.
All right, thank you, Rania. So as Rania has introduced previously, we've considered a couple of long-term conditions, but as part of our research in DECODE, we also look at the concept of hospitalization, because the hospitalization data gives us insights as to the criticality of some conditions. So we're able to merge like about 110 conditions into 40, but not all those conditions required hospitalization. So in this talk, I'll just address a couple of analysis that was done on hospitalization data for patients in Wales. We identify a couple of common conditions treated in hospitals and top primary conditions as well. We identify some conditions that were very prevalent with long hospital stays. And we also explored the use of machine learning models to predict the length of hospital stay. When we get there, I'll explain the reasons and the purpose for this analysis. In addition to the machine learning predictions, also we addressed the transparency of these models in the sense of how equitable these models are in predicting across sensitive groups. And for our study, we looked at the sensitive group of ethnicity. So first, with just demographic information for the hospitalization data with the cohorts that we studied, it comprised of 4,929 males, and across these males, there was a distribution of 32,000 plus of unique admissions. This was between 2000 and 2021. For females, it was 4,600, which is, it's lower than that of males. So the males had more hospital admissions as compared to the females. Looking at the distribution with regards to the socioeconomic index, we look at the Welsh index of multiple of deprivation, and what we observed is that the hospitalization rate increases with deprivation. So what that means is in most deprived regions, there were more hospitalizations, and it reduced. So it's when you get to the point where it's least deprived, the hospitalization rate is little, which is expected as in compared to other previous researches. So one reason for this might be probably for most deprived regions, there's not that easy access to healthcare, or in most cases, they might not have enough resources to help, that they only get to hospitals when it's really critical. So they get admitted into hospital for critical cases. So we also see that there's the group called unknown. Usually in research, people would try to remove this samples or these patients from the study, but it's a good thing most times including this, because this actually helps us to model normal real life situations, because from what we have with EHR data, not all patients would choose to declare their ethnicities. For instance, not all patients will declare their index of multiple deprivation. So with the age group as well, what we see a normal distribution for males and females. An important thing we observed here was there was a significant drop in the number of hospitalizations after the age group of 60 to 69. Trying to look deeper into this, we compare this also to, this can be due to different reasons. It could be probably the patients are able to get home care, or mortality can be actually a strong play in it, because from the initial introduction from Georgina, we see that the mortality rate for adults with learning disabilities is around that space of 60 to 69 years. So on the average, around 66 for males and females. So after that age, there's a much reduced number of hospitalizations. So looking at the common and primary long-term conditions. So I'll just explain what I mean by primary. So with the SAIL data sets that we observed first, they have SAIL uses the PEDW, that's the patient episode database for Wales, which it records all hospital episodes, and they have a variable called the diagnosis number. So the diagnosis number, it ranks the different conditions that a patient is treated in hospital from 1. So that number 1 relates to the primary condition for which the patient was admitted. Then the other conditions are the secondary conditions. So for the primary conditions that led to admissions for males and females, you see that cancer was the top. For males, followed by epilepsy, chronic pneumonia, chronic airway disease, and mental illness. For females, the primary condition was cancer, chronic kidney disease, epilepsy, chronic pneumonia, and chronic airway diseases. So like Rania said initially, the chronic airway disease is not just a single condition, but it's a group of conditions. It includes asthma, bronchiolitis, and some other airway related conditions. For the common conditions, this includes both primary and secondary conditions. So it's just it's a total. We're looking at the total of all unique cases for which a patient was treated, like the different conditions with all the different previous admissions. So epilepsy was the top, which also correlates with MenCap results. So epilepsy is one of the top reasons for hospitalizations, followed by diabetes for males, chronic airway disease, mental illness, and cancer. For the female is chronic epilepsy, chronic airway disease, diabetes, thyroid disorders, and mental illness. So looking further, we tried in our study to also observe some outliers. We looked at the length of hospital stays, and we tried to look at outlier stays, like stays that were very much long. We obtained this threshold of 129 days by looking at, we created a box plot of outliers, and we looked at the upper whiskers. So we're trying to get an example just to show for this presentation. So we looked at admissions for which the patient stayed longer than 129 days. Mental illness was the top, with 61% of admissions related to mental illness. Epilepsy follows with, and diabetes, dementia, and cerebral palsy. One of the reasons why mental illness is the top would be because most of these cases, these admissions will relate to patients in long stay hospitals, which is expected. So they would tend to stay longer during admissions. The other conditions, what we observed, also looking at the age distribution, we see for patients who were admitted and who stayed long in hospitals that did not have mental illness, majority of them were skilled older. So what this means is for most conditions which patients stayed longer than usual, probably the conditions were linked to old age. So that's why we see conditions like diabetes, dementia, cerebral palsy, and the rest of them. Looking further, so we tried also to observe trends. We just looked at some common recent news in 2014 alone. There's a couple of news having to deal with hospitalization. This news actually correlates with the general public, but majority of the impact of these findings actually affects adults with learning disabilities. And just to summarize this news from The Guardian and also some research done by the University of Birmingham, we address a couple of severe cases dealing with hospitalization. One of them is premature discharge, where a patient is discharged earlier than necessary. And most times this could lead to serious cases, probably mortality, preventable death, which at homes, or high and increased rate of readmission, which was reported by The Guardian, which I think this year alone, there was about 2,000 of mental health patients readmitted within a month of discharge. On the other case, we're looking at patients stuck in hospitals. So it's a common scenario where we find with mental illness patients staying much longer than normal. That also has a disadvantage where the patients it's possible to acquire more conditions that can be contagious, maybe from hospitals and the rest. So what we try to do with this information is to explore ways in which you can manage patient hospitalizations. And to do this, we try to look at the machine learning models to see how machine learning can actually come to play in this. I've actually introduced this in the previous slides. So 2023, there was 5,000 people readmitted into mental health facility within a month of living in England. 2,000 patients, this was from a research in Birmingham, 2,000 patients with learning disabilities and autism in long-stay hospitals were hospitalized, with over half of them spending more than 2 years in hospital care, which includes about 350 that spent more than 10 years. So for our research, predicting hospital stay is a complex thing because, like, when you consider every individual has the conditions for each individual varies from the other. So instead of predicting, making a continuous prediction, like to predict for each individual how many days can this person spend, what we try to do is to break down the broad problem into creating a binary prediction. So with a binary prediction, we try to find a threshold of length of hospital stays by looking at the distribution of hospital stays of the patients in our cohort. And with this threshold identified, we can have a binary prediction to classify patients who would stay less than those days or patients who would stay longer than those days. Our threshold in this study was obtained by looking at the mean of the distribution. So we take the ceiling value of the mean. The ceiling value is just the minimum integer that is greater than the mean. So for a mean of 3.0515 days, we obtained a ceiling value, which was our threshold of 4 days. So our study involved the use of machine learning models to classify stays below 4 days or stays greater than or equals to 4 days. This was the inclusion criteria that we used to clean and prepare the data for the machine learning models. So for this study, we are looking at patients that are adults. So we exclude all patients who within our study date of year 2000 to 2021, any patient who is less than 18 years, not registered with a GP, and does not have any diagnosis of learning disabilities during our study period, those patients were excluded. So that gave us, from number 4, we see 14,000 patients. And we further extracted the patients that had at least one hospital record. And we also went further to do further cleaning of those data. A couple of these EHR results are very noisy in the sense that some of them had missing discharge dates. Some of them had negative duration of date. So what that means is the date of discharge was much earlier than the date of their admission. So for those results, we had to exclude them from our analysis. And the plan of this study was to make initial predictions. So we only used the first information up until the first 24 hours of admission. So those patients who didn't have any information within the 24 hours of their admission, they were also excluded from the study. So a couple of variables were put into consideration. We considered the BMI, smoking history of the patient, alcohol history, physical activity, autism. The previous admission as well was taken into consideration. We also looked at the number of episodes within previous admissions. So we considered both historical data and current data up until the first 24 hours. We also had binary variables for each condition to indicate the multiple long-term conditions that each patient had. And this was used to help predict if a patient would stay less than 4 days or greater than or equals to 4 days. We compared about 8 machine learning models for this. The random forest actually gave a good performance. But what we did again, using the random forest, we tried to look at 3 different performance matrices. One is the false negative rate. So a false negative rate would refer to those cases where our model predicted that the patient should be discharged early, when the patient, on the other hand, actually needed to stay longer in the hospital. The false positive rate would refer to cases where a patient was predicted to stay much longer, whereas the patient should have been discharged. So to avoid the patient false positive rate helps to identify the number of patients that are unnecessarily staying long in the hospitals. The balance accuracy just helps to see how well the model predicts both the positives and the negatives. So for our case, the best operating model, which was the random forest, had a balance accuracy of 0.6, and that's 69% for the males, 68% for the females. But again, for transparency, because when explaining the way machine learning works, we want to also be transparent to how it operates on the data across sensitive groups in our cohort. So as much as this performance looks okay for the overall data, we also try to look at how this result is distributed, how the result behaves across the different ethnic groups in our study. So what we observe from here, if you look at this chart I'm showing right now, we have the 3 different performance matrices. We observe that the performance is not the same for all the ethnic groups. So one close thing to observe is that the performance for the whites group, for instance, is very much close to the overall performance of the 69% for the balance accuracy. Same applies to the false positive rate and the false negative rate. And one reason for this is because the white group it contributes to about 80% of the entire data, which is expected. So what it means is the model has enough information of the white group, also the unknown group, the Asian group to a certain extent, for both male and females. It has enough representation across this group such that it can observe the patterns for patients within that group. But that doesn't mean it's necessarily operate well for the other groups, like the Blacks, the other groups, for instance, they have a very high level of false positives and false negatives, the same we observe for the other group. So what we try to do as well in this work is it's good to be transparent with the result and show the limitations of this model. And also we try to apply bias mitigation algorithms that would address these imbalances. So the aim of this balance mitigation algorithms is to try to reduce the discrepancies across the different ethnic groups. For our study, actually several algorithms that could be applied, but for this study, we used the threshold optimizer and the exponentiated gradient. I think I had a talk last year in September where I explained a couple of this, but because of time, I may not be able to explain this difference in the different algorithms. But the threshold optimizer works in the post-processing state, that is like after training. It's often used in cases where if the researcher doesn't have access to the data, maybe due to security reasons, for instance, SAIL doesn't disclose all their, you wouldn't have access to the SAIL data without permission, but it's still possible to actually mitigate the errors or the bias with the way the model operates. So this is good in cases where you don't have access to the direct data. Exponentiated gradient works during training, so you have to have access to the training data and also the model itself. So just to observe how these models work. For the males, the first results we have unmitigated refers to the random forest without any bias mitigation. Then the two results, we see the threshold optimizer and the exponentiated gradient. The aim, like I said initially, is to reduce the discrepancy. So we're trying to reduce the performance range, which is the difference between the maximum performance metric and the minimum. We observe for males that the threshold optimizer doesn't really work well in reducing the range for the false negative rate. Compared to the unmitigated, but the exponentiated gradient works very well because it reduces the difference very, very well, significantly. However, for the false positive rate and balance accuracy, the threshold optimizer works very well in reducing compared to the unmitigated method. However, the exponentiated gradient doesn't really work well. It's actually increasing the differences, so it's not giving a good performance. For females, on the other hand, threshold optimizer works well compared to the two other algorithms. However, it doesn't work well for the two performance matrices, the false positive rate and the balance accuracy, the exponentiated gradient as well. So we see that this data, based on the data we have, the algorithms works much better for the males compared to the females. In conclusion, for what we just did, we've looked at the data, hospitalization data of about 9,000 patients. We observed cancer was a top primary condition for hospital admissions in both males and females. Epilepsy was the most common co-occurring condition across all admissions between 2011 and 2021. For hospital days above 129 days, most of them were related to mental illness. We observed the random forest model, which I just showed initially, using information up until the first 24 hours of admission. And we had addressed two bias mitigation algorithms to obtain equity in the predictions of length of hospital stay. In another study which we did, we are observing identification of clusters of long-term conditions. So clustering is actually, I'm sure a couple of people here have studies that are addressing clusters of multiple long-term conditions. So the concept of clustering has actually been applied in a lot of medical related research. It has actually led to a lot of advancements in diagnosis, symptom management, prognosis of complex diseases such as cancer, diabetes, cardiovascular diseases, and the rest. It actually has a huge advantage in helping to advance personal medicine, predictive modeling for unique patients and all. But one thing we observed during our study is that there is very limited research on clustering to analyze the patterns of multiple long-term conditions among individuals with learning disabilities. So looking how disadvantaged this cohort study is, we just realized the need for an efficient clustering system to identify those patterns. So in our work, we also use SAIL data sets, which comprises of 47% for females, 52% for males. We looked at about 6 machine learning and statistical clustering algorithms to identify the different clusters. One important aspect of clustering, because our work is an unsupervised clustering approach, so we don't really know the optimal number of clusters. Since it's an unsupervised model, so we have to apply a couple of algorithms to identify the optimal number. So a couple of approaches were used. the silhouette width, elbow heuristics on the sum of squared errors, the BIC, the Bayesian information criterion. When we observed all the 6 algorithms, we observed that their optimal number of clusters were usually between 3 to 4 clusters. So we selected the algorithm that had the highest separability in the case that the clusters were not overlapping and they were not so much noisy patients within a certain cluster. So for the male, the 3-cluster Gaussian mixture model operated better across all other algorithms. For the females, it was the Birch. So this is just a summary of what we identified. For the males, the work was able to, our clustering approach was able to identify 3 clusters. The first cluster had 100% probability. So this is a probability plot for all conditions that we considered across clusters. So had the highest, that's 100% certainty of reflux disorders for patients within that cluster, was followed by mental illness, medium probability, that's about 38% for mental illness. So this cluster can be termed the high reflux, medium mental illness. Cluster 2 was patients have high probability of cardiovascular and respiratory conditions. So this includes heart failure, even chronic kidney diseases, chronic airway diseases as well. For the third cluster, which was the highest cluster, it had the highest number of patients, 4,200. This is the relatively healthy clusters. So it had very low probability across all conditions. However, we see that epilepsy and mental illness was had the highest probability across all other conditions. And like we've seen from the previous slides I showed, mental illness and epilepsy is actually one of the most prevalent conditions for adults with learning disabilities. For the females, we identified 3 clusters as well. So the largest cluster with 5,000 patients also, we termed that a relatively healthy compared to the other clusters where the percentages were less than 50 for all. And again, it was still, there's epilepsy and mental illness still had some level of high probability compared to the other conditions. For cluster 2, we defined this as the high reflux disorder, mental illness, pain, and respiratory conditions. The cluster 3 had a high cardiovascular and respiratory conditions. So the thing about these clusters we've identified, the further work we will aim to do is to identify different characteristics of patients within each cluster. We look at the associated risk factors. We look at the demographic distributions as well. Intuitively, one could look at the healthy clusters and we could say probably most of these patients are young, because from our study, the number of conditions or the number of morbidities increases with age. So for those cases where they are more healthy, they have less probability, they could be younger. So, but we would look deeper to get more clear statistic on this work to obtain demographic results, risk factors, look at medications that they observe as well. And also another further thing that could be done is observing trajectories of conditions across the different clusters. So that would help to drive an understanding on disease progress. We could further look at predictions for each patient. We could predict what cluster does a patient belong to, what is the probability of the patient having another condition in addition to what the patient has. So I'll leave that now for Rania, who would explain a couple of points from her study in multiple long-term trajectories. Thank you.
Thanks, Emeka. Thank you very much. Can you move to the next slide, please? Yes. So the long-term conditions like diabetes, asthma, arthritis, and others have a significant proportion of the population in long-term conditions and often appear together. Managing learning disability patients with multiple long-term conditions is challenging because the unique progression of the comorbidities over the time, because they have many long-term conditions, is crucial. So traditional approaches may fail to capture this complex temporal progression in the direction of the diseases. So there is a need for innovative methods for better understanding the temporal patterns and the relationships among the long-term conditions to predict patient outcomes like mortality or hospitalization, like Emeka explained, and personalized patient predictions to the unique needs of different patient subgroups. So our aim is to address these challenges by using statistical and machine learning techniques in order to develop long-term condition trajectories that take into account the temporal directionality and uncover the patterns among these trajectories. So initially, we began by creating trajectories using statistical methods that capture the sequence of diagnosis of the patient over time. In this example, as it's shown, some patients progress from diabetes to asthma, then hypertension, arthritis, and eventually retinopathy. Others may follow a different path. In these two trajectories, we can see that share a pattern that characterized by endocrine and cardiovascular conditions. So we try to develop a machine learning model that group these trajectories that share similar diagnosis patterns over the time. In this time, we are exploring different approaches and we're trying to find the best model that gives us the better clinical results. Except of this clustering, we investigate the cluster association with important outcomes for this population, like mortality and hospitalization. I wanted to mention that in the whole analysis, we employed clinical experts to validate the clusters and see if that makes clinical sense. Thank you, Emeka. To conclude our discussion on the next steps, the CPRT data are almost prepared, and by analyzing the CPRT data, we aim to validate and extend our findings in SAIL from the initial work, and the defining shared temporal patterns of multiple long-term conditions in England will further help us to understand how these conditions interact and progress over the time. Looking forward to present this as soon as it is finished. And in conclusion, the next slide, Emeka, thank you. I'd like to say that this research will help healthcare providers to understand disease progression. For example, given a patient's profile, we can identify trajectories closest to this profile over the time, in addition to address premature and avoid mortality using trajectories to prevent a most likely next condition to happen. And last but not least, to effectively managing resources by reducing hospitalization and excessive lengths of stay. Thank you very much. Any questions, please? Thank you.
Thank you.
Thank you. I would like to thank Georgina because she's been answering questions in chat throughout the talk. So thank you for doing that. But we have a couple more questions, and since the talk is now finished, we will finish the recording. So feel free to raise your hand and ask a question directly.